Hi everyone, today we're going to be talking a little bit more about the reverse chain rule. Now, in our last video, we proved this identity here on the formula sheet by showing that if we differentiate this right-hand side, we will get the thing that we are integrating. And because integration is the antiderivative, this shows that this essentially holds. But the thing is, we can actually apply this idea of the reverse chain rule to all the functions that we have to learn for the advanced mathematics syllabus, being e to the x, log of x, and the three trig functions. Now, we'll look at log in a second because that one's a little bit more complicated, but for the other four, it's actually relatively simple because if we're given, let's say, y equals e to the ax plus b, 1 on a, then, and we differentiate it, then dy on dx is equal to, well, we take the derivative of this, we should remember from the chain rule, so we go a times 1 on a e to the ax plus b, which is just e to the ax plus b. And so from this, we can therefore say that the integral of this is going to be the thing we started off with. There we go. And it works in a very, very similar way for the other three, for the sine, cos, and tan. But I think it's best illustrated by sort of just getting into some examples, and you'll see that the reverse chain rule is applied in very much the same way throughout. But you'll notice that with each of these four, we still require that that inner function be linear. We still require it to be in the form ax plus b. Okay, so getting straight into the examples. Here's a couple of things that I didn't cover last time out, but actually still fall under the category of that first rule, ax plus b to the n, and integrating this one here. And I'll show you why. It might not be immediately obvious, but we can actually rewrite these as integral of 3x plus 5 to the power of a half dx. Right, and once we've done that, this half, we can treat that as any other n, yeah? We don't care that it's a fraction. So what we do is we, first off, we got to multiply by 1 divided by 3 times, and then we increment this power to the 3 on 2, and we've got to make sure we divide by that as well. Yeah, this new n plus c. So to simplify, bring this to the top, and we go 2, 3x plus 5 to the 3 on 2 on 9 plus c. And then that's that one finished. Exactly the same deal for this next one, even though it's on the denominator. We can rewrite this as 6 outside of 2 minus x to the power of negative a half. And so even though this is a fraction, even though it's negative, it's still, a number n, so we can still treat it in the exact same way that we would the other ones. And so we go, this 6 we don't worry about because it's a constant, so we just leave it out the front. Should write that. So 6 times, and now 1 divided by negative 1, which is just negative 1, times 2 minus x to the power of a half, and we divide by that new power plus c, and then we go, so negative, and then this 2 comes up the top, so 12, 2 minus x to the power of a half is the same as root 2 minus x, so root 2 minus x plus c. And for these first two, again, to test it, you can just simply differentiate these and you will obtain the original, the thing you started off with. Okay, now pressing on to our new examples. We've got a power of e and we've got sine of a linear function. And so these ones, I mean, there aren't really many steps, but if we look at this as, you know, e to the ax plus b, well, b is 0, a is 3, so the answer is going to be 1 on 3 e to the 3x plus c. No tricks here, nice and simple. Same with the sign. I mean, in this case, a equals -1 and b equals 1. So a is negative, that's the only tricky thing. And so what we'll get is, so 1 on -1 times. Now don't forget, the integral of sine is negative cos, because the derivative of cos is negative sine. And so we'll get negative, and that does reflect itself on the formula sheet, you'll notice here. Because if we were to differentiate positive cos, we get negative sine, so one side has to be negative in that relationship. So negative cos of 1 minus x plus c, and so the two negatives cancel and we get cos 1 minus x plus c. Brilliant. So that's that done. Hopefully that's in enough detail. Now the next bit is the logs, which is a little bit more complicated. So what I just want to show is, if we have y equals log of any function f of x, and we want to differentiate that, we'll get dy on dx from our chain rule equals the derivative of this out the front, so f dash x, times the derivative of the log with respect to f, right? So what we're actually doing here is, this is dy on dx equals dg on df times df on dx, where g of a function, or let's say g of t or something, g of anything is equal to log of it, right? And so in this case, we've got g of f, and then f of x is going to be you know, itself, because we're not specifying what it is, right? So it doesn't really matter. So if we differentiate this g dash, it's going to be 1 on the thing that we're differentiating with respect to. So what we'll get is 1 on f of x. Now, if that's a little bit confusing, I suggest going back and watching the video on the chain rule. It's tough to get your head around at first, but once you sort of understand it, and it is understood through watching applications as well, it becomes a bit more clear. But essentially what we end up with is, we end up with this groovy little thing where we've got the derivative of some function divided by that function, right? And then the exact same way that we proved the other reverse chain rule ideas, well, if we integrate this, then it's just going to be log of f of x plus c, right? Because if we can differentiate, forgetting all that, if we can differentiate log of f of x and end up with f dash x on f of x, then by definition, if we integrate f dash x on fx, we have to end up with log f of x plus c, right? And so this ends up being really, really powerful, and you've got to learn how to be able to spot this, because they expect you to be able to do this slightly more difficult example than the other functions. The reason this is more difficult is because it doesn't have to be linear. Note, fx does not have to be linear, right? So getting into some examples over here, a linear example would be just like, what is the integral of 1 on ax plus b, right? Which is relatively simple when you think of it. It's going to be like 1 on a log ax plus b plus c. So these integrals here we can all do by applying this formula. So we notice up the top, it gives us a bit of a hand. By expressing the following as f dash x on f of x, find these integrals. So in the first example, it's already pretty much done for us. If we let f of x equal x squared plus 3x plus 7, then f dash x, or df on dx, is going to be 2x plus 3, right? So therefore, the integral is simply going to be log of x squared plus 3x plus 7 plus c. And that's the answer to this question. The next one's a little bit tricky to spot, but if you think about it, if f of x is equal to e to the x plus 1, and then we differentiated that, well, e to the x derivative is just e to the x, and 1, well, the derivative is 0. So we actually do have this already in the form f dash x on fx. So the answer to this integral is going to be log of e to the x plus 1 plus c. This one, a little bit trickier. What we have to do is we have to recognize that this is actually equal to 1 on x on log x dx. And then when we do that, it becomes really clear, well, if f of x is equal to log x, so f of x is equal to log x, then f dash x is 1 on x. So therefore, the integral is going to be log of fx, which is log of x plus c. And again, you differentiate these using the chain rule, and you'll find that you get the thing that you were integrating in the first place. Finally, tan x dx. This one is one of my favorites. What we have to do is we have to write this as sine x on cos x dx. And we'll actually rewrite this as negative sine x on cos x dx, because now if we have let f of x equal to cos x, then the derivative is equal to minus sine x, right? So that's why we're making it minus and bringing a negative out the front. So therefore, the whole integral is going to be negative log of cos x plus c. All right, I hope you guys found this helpful. Again, reverse chain rule is best understood by doing lots of examples and really testing yourself on it. Okay, thanks for watching, and bye.